All right, so we are going to continue a little preparation as it relates to the CSEC chemistry exam. We're looking at the topic organic chemistry. And so again, I'm Mr. Thomas. Welcome to Buckle Down. This is a video from our live class. All right, I hope you will learn something and find it very productive. So one of the things, the past class, we were looking at these organic structure. These organic compounds were basically listed, and we are supposed to deduce certain information from them. Now, just going to run through some general things that we should be knowing at this time. All right, so these are things, recap, that we should know. Just let me pause a second. One of the things, and I just running, and I will be going maybe fast. If you have a question, you can stop me. One of the things, hydrocarbons. We said that hydrocarbons are basically compounds that can contain hydrogen and carbon only. But along with that, we have organic compounds. Now, organic compounds, typically, the foundation is carbon. So compounds that comprise of carbon. The thing is, we have a few compounds, even though they contain carbon, they are not organic. And one such compound would have been carbon dioxide. Now, if you look back, or if you are a student that is doing biology, when you talk about photosynthesis, they would have said an inorganic substance, which they're talking about water and carbon dioxide. So even from that point, we know that carbon dioxide is inorganic. It's not organic. The other set of compounds that are not considered organic, even though it contains carbon, would have been carbonates. So all the carbonates, calcium carbonate, magnesium carbonate, those are not considered to be organic compounds. Now, where do we get these compounds from? Where do we get hydrocarbons from? There are two sources that we can get them. One, natural gas. So naturally in the environment, we can get these compounds to basically be utilized, because you know that man has actually figured out from past time that they can use these for various uses. The other area that we can get them from would have been petroleum. And you know, petroleum, another name for it is crude oil. And we know the background in terms of how organisms would have died. They break down and they stays for a long time within, and that's why we consider that to be a non-renewable resource. Now, crude oil is typically a mixture of different substances. Now, when you think about a mixture, you know that these are substances that are in the same space, but they are not chemically combined. They're not chemically joined to each other. And so, for crude oil, what humans have done is to get the different fractions of it and use it in different industries. So crude oil is a mixture of different components. It's not only one. And so what we have realized is that now that man knows that, this crude oil is very useful. And we've seen, I'm going to pause a second. All right, sorry about that. So we said that we as humans recognize that we can basically use the crude oil for various purposes. Now, remember we just mentioned that it's a mixture, and a mixture you have different components, but they are not chemically combined. And so you can separate them using physical techniques. And so when we want the different fractions, the different components in crude oil, what we would have done is to carry out a process known as fractional distillation. So we go to fractional distillation. Now, fractional distillation, the concept of it is that different components within a mixture, and if I didn't say it, crude oil, of course, is a liquid. So different components are within the liquid. And so we use fractional distillation because what we can now achieve is to place the crude oil in a chamber and then we heat it. So when we provide heat, the crude oil, just like any other liquid, will basically become a gas or a vapor. And each component, based on the number of carbons that it has, would have had a different boiling point. And that is what we use to separate the different components. So we use fractional distillation and we get several components. You can look at the process we have done looking through how we get the different components. We also have a situation where in the whole fractional distillation process, we tend to get long hydrocarbon chains. So the chains that we're getting, we can have up to more than 30 carbons in the chain. So from 1 to 4, we know we consider those the refinery gases. So like your butane, your propane, your methane, your ethane, those are actually the ones that are benefiting majority of us. And I have said this in several classes, while we may have persons traveling overseas taking an aircraft, because one component of petroleum is also kerosene, which is the fuel for jets. Not everybody, not every country, not you have some persons who have never gone on a plane. So technically that is not something that is affecting their daily life. But even if you don't cook at your home, you may be purchasing something from KFC, you purchase something from a cook shop. These persons would have more than likely be using one of the butane or the propane in their cylinders to prepare your meal. So indirectly, it affects everybody. And so, again, while we do fractional distillation, man realize so the components then we are get, we're not getting enough of the ones that we're utilizing on a daily basis. I'm sure persons probably start pressure them peas, them parents start pressure them peas or them start cook already. And all of that is done because you have the liquefied gas inside of your cylinders, your propane coming from your IGL or your gas pro, and that is a component of crude oil. That is the component that I am saying affects more persons. So why is it that I'm mentioning this? Because sometimes they ask the question in terms of cracking. Now, students often get the terms mixed up. Cracking is different from fractional distillation. So fractional distillation, you separate and you get components that can have up to 30 carbons. Now, as I said before, these long chains of carbon compounds, they're not the ones that are going to be benefiting everybody. And so to a follow-up, we do the concept of cracking. And the term is very simple because all we're doing is to break down longer hydrocarbon chains into smaller ones. So those long chains, and remember the smaller ones that we're talking about are the ones that would have been beneficial to us in our everyday life. And again, it's not that the others are not important, because one of the longest chain has 30 carbons, and even now currently we see them making patches to the road. And that aspect, the asphalt, that is a component of our crude oil. So it affects us in terms of the road network, getting to from point A to point B. So it's not that the others are not important. They are important, but influencing. Because if I can take that as a situation, you have some places, even in Jamaica, that don't have a road and a road network. So yeah, 2025 it shouldn't be, but some roads though are just not there like that. And so it's not benefiting, but more than likely somebody has a little gas stove. So they need something to prepare. They can use that for heating. So cracking, what it does is to break down the longer hydrocarbon chains so that you can obtain the shorter ones, which are more useful to us. When you get those shorter ones, when you operate or carry out cracking, you will get a alkene. You must get an alkene. And what's an alkene? If you don't know, it's an organic compound that has at least one double bond. And see an example here, right here in A. So we're seeing this double bond between the carbon atoms. So every time you crack, sometimes CXE asks you to crack a compound. Remember, you're cracking it so that you get at least carbon compounds that having 1 to 4 carbons. And when you get those carbon compounds, one of them, at least one of them, must be an alkene. So there are various ways to demonstrate cracking, but the basis is one must be an alkene. So just draw. So even like this, let me just use this for an example. 1, 2, 3, 4, 5, 6, 7, 8. This is an 8 carbon compound. And we said that ranging, I can get a 3 carbon compound. And this 3 carbon compound, I'm going to single out this one to be my alkene. From that, I know I wouldn't use and say that the other carbon compounds would be 5, because we said that the main ones that we're going to be utilizing would have been 1 to 4. So again, I can break up that 5. I can get another 3 carbon compound. This time it is an alkane. And I can also get a 2 carbon compound, which is also, sorry, this shouldn't be a plus, which is also an alkane. So the aim is, and there are other ways you could have cracked it. You could have gotten a 4 carbon compound as your alkene, and then of course you can get one carbon compound, methane, and you get another 3 carbon compound with his propane. You could have gotten 2 alkenes and 1 alkane. But again, the basis or the principle that you need to remember is that you need to get at least 1. So when you're demonstrating, when CXE, if CXE asks you to crack a compound, they give you it, they are going to be looking for you adding 1 alkene to the mix. Cool? So thermal, as you hear the word thermal, you know you're thinking about heat. And so what they do is to bring, in order to break the bonds, because you see this thing is a rich mixture of different compounds. The hydrocarbons that are there, right? They would have created, the longer the chain. So the more carbons you have, the stronger the bond. So that's why even when you look at fractional distillation, going back to that, the crude oil has to be put at about 450 degrees Celsius. When you put your finger in a little water with upon the gas stove, I test if it hot or something, accidentally you sip in your tea and you just basically maybe burn your tongue or your lip or somewhere and you feel that degrees. Remember, say the tea would have come off of the stove for a little while, so the degrees start go down. You know, they're 100 yet. Think about 4 times that. That is what they have to put this liquid at for it to break the different chains. Because remember, break here, break the bond them, you know. So when we are crack, we are broke up. So forget the one alkene and the other rest are shorter carbons. We need high temperatures. So we basically do thermal cracking. The other one, catalytic, same as having high temperatures, but the catalyst helps to let the reaction move faster. And so I can pause here. One of the things that one topic is green chemistry. Green chemistry deals with preserving the environment, still doing what we're doing, but at the same time, think about the environment. So while we crack and do all of this to get or obtain the useful carbons, that takes energy. The cracking itself takes energy, you know, right? And so you don't want to be burning a lot of energy. So the more ideal way to do the cracking under green chemistry, you know, people say go green, is to use the catalyst because the temperature is not going to be as high and the reaction would have happened much faster. Yeah, so you reduce the amount of energy. That's the whole concept of green chemistry, preserving the environment while we still have these chemicals and things that are making our lives, you know, much easier. Now, in this concept of organic chemistry, we refer to a group as being a homologous series. Now, each homologous series have certain characteristics. Once I'm part of a homologous series, all of us, so one characteristics, all of us have the same general formula. So they like to ask questions about this. So all of us have the same general formula. So quickly, what's the general formula for an alkane?
C2HN. No, CH2N. One of them.
So the general Cn, you even make me right what you say. So Cn H2N plus 2. Very important. So every homologous series, that's an alkane. So every alkane, and I want to again make reference to the fact that sometimes they ask you, you get a compound like this. And bear in mind, sometimes when I'm going through, I may not show you the hydrogens, but as an organic student, as a chemistry student, please bear in mind that the hydrogens are there. So it's typically done because of interest of time. But if you get this compound, right, And CXC says, what homologous series does this belong? And you say propane. Will you get the mark?
No, sir.
So you would not get the mark because, again, the question is targeted at the name of the homologous series. They didn't ask you what's the name of the compound. So please, you have to ensure that you're checking the questions and answering what they ask. So some students just jump and see this and just automatically just start write, hey, this is propane, not realizing that it says homologous series, so you should write alkane. So every alkane, even this in this example, all of them will follow the same general formula. Everybody, Cn, where N is the number of carbon. So 3 carbons, right? So the molecular formula for this would have been C3H, so 2 times N. So automatically we know 2 times 3 is 6, plus 2, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And so even when you're going through, if you don't, you have to be back and forth, guys. The back and forth meaning the name, the structure, the homologous series, the general formula. You should be able to go back and forth between them so that you can actually, once you've mastered that, you would be good in terms of most of the questions and interpreting. Because if you don't know what the compound is, every compound that we deal with has a basic way of how they react, right? And so once you know it's an alkane or an alkene or an alcohol, then you should be able to better answer the question. So every homologous series, they have the same general formula. Every homologous series, they have the same functional group. So even though I didn't mention the functional group, sorry, even though I didn't mention the general formula for the others, we should know. So what's the general formula for an alcohol? General formula for an alcohol. Anyone?
So CnH2n plus 1 OH.
Wonderful. So you should know this. And again, if you quickly draw one, the application of you being able to reason out. So bear in mind, we don't consider the OH. The hydrogen in the OH, we don't count it in the number of hydrogens here. So again, even if I see where carbon, we have 4 of them, automatically I know it's 2 times 4, which is 2 times 4
8,
plus 1.
9.
So right there and then, you can use that to double check, because sometimes you can make a little mistake, you can make a mistake and leave off a hydrogen. So at the end of the day, the general formula is a guide as well to highlight if it is a particular homologous series you're dealing with. So you can get the name. So anybody knows the name of this? What's the name of this?
Butane.
Huh?
Oh no, I didn't say the OH. Butanol.
So butanol, and specifically 1-butanol or butan-1-ol, because the OH, which is the functional group, is on the first carbon. We have to remember those things. So if CXC says 1-butanol, you should be able to draw the structure. You should be able to tell the general formula. You should be able to write the molecular formula. So all of that is very important. All of them, as you add one carbon, you're really adding a CH2. So we going in the homologous series, prime example. If I look at the first series in the alkane, who is the first person in the alkane? Let me not say person, but the first compound. First compound.
Sir, Nathan.
All right. So I'm going to show you why we said that we add a CH2. So if it is, we go in here. When we add this for ethane, we're technically adding, what are we adding? So look, because person will probably attack me. Technically, the methane had how many hydrogens to carbon? How many hydrogens and how many carbon?
Sir, one
So the
carbon,
meth,
four hydrogens.
all right. But as you increase the number of carbons, C2, we're going to have H, how much?
8.
Sure about that?
Uh, see. 6.
All right. So watch me now. If I am to really show and I can use this. Remember this part of it would have really represent. I'm just using this as the part to show you that this is would have been the methane itself, if you want to categorize it like that. So for ethane, what we actually did, as we said, we just basically were increasing by a CH2, and that's for every organic compound. So every homologous series, the next person in the series, which would have been who? Who is, and I keep saying person, but bear with me. The next compound in the series would have been who? So if me have methane, ethane, who's next?
Propane.
So propane would just be adding a CH2, and you can check it and see if that isn't the concept that you're doing each time. So each time you're adding a CH2. CH2. So for every homologous series, and this goes for the general characteristics, everybody is the same, whether you're an alcohol, whether you're an acid, whether you're an alkene, whether you're an alkane, again, you're going to be adding a CH2, and this will help you guys. So if you technically know the names or the prefix, just remember you're adding a CH2 to the following compound. Everybody has the functional group. You cannot be called an alcohol and you don't have the hydroxyl group. You cannot be called an alkene and you don't have the carbon to carbon double bond. You cannot be called an acid and you don't have that acid functional group. And we said that for the acid, either of these ways, we need to remember them. So either of these would have represent an acid. So once you're seeing these, you know. Well, not finally. We have two more other points. Everybody have similar chemical properties. Why do they have similar chemical properties? Because here's the thing. The functional group is where you have reactions occurring. So everybody has the functional group, so everybody is going to be reacting in the same manner. So chemical properties are similar for everybody. So whether you're methane, whether you're ethane, whether you're octane, if you're to undergo a reaction, all of you are going to do it in a similar way. Same for the acids, same for the alkene, same for the alcohol. Everybody. So that is it. That is why when we're giving examples, so I may give you an example of, say, alkene reacting with hydrogen. It doesn't matter if I change the alk. So if I say ethene, you should be able to show the reaction with butene, propene, hexene, heptene, whichever ene, because all of them react the same way. So once you know how to react an alkene in the sense of reacting it with hydrogen, it doesn't matter. It shouldn't confuse you whether CXC send propene or ethene. You should know the outcome because everybody react the same or similar. And then finally, because you're adding one more carbon each time, there's a slight difference with physical property. So physical property includes like melting point, boiling point, density, solubility. Those things will vary because you're adding more carbons. So while the chemical properties stay the same, the physical properties are different. So sometimes, majority of the papers, what I see them ask is to list three properties. And you can be going through the past papers and you meet upon these questions. They would say, what are general? And we said general meaning we're not only limited to alkene and alkane and alcohol. Every single homologous series. So everybody who is in the series have the same general formula. Everybody who is in the same homologous series has the same functional group. Everybody, as we increase, going up, adding one more we're adding a CH2 as we increase. Everybody has similar chemical properties. Everybody, there's a slight difference in the physical properties because we're adding a CH2. So those are the general characteristics of the homologous series. Any questions? Ask you. So once they ask you about burning, and it doesn't have to be only the alkene or the alkane, but they also can ask you to burn the alcohol. So for this, they did say, write a balanced chemical equation for the reaction occurring when C burns in excess oxygen. So C we're targeting, but I'm going to run it for both A, B, and C. Usually they don't burn the acid, right? So the burning is really condensed to these three organic compounds. So we're starting with We can start it with A. So what's the molecular formula for A? Molecular formula for A. What them there? What's the name of A?
Butene.
And as I said, we have to, if we be specific, 1-butene. Yeah? So what's the molecular formula?
C4.
C4H8.
Wonderful. And at this point, cheat code, once you have an alkene, the hydrogen is always just twice the carbon. So if the hydrogen would have been 10, the carbon must be 5. All right? Because it's 2n for the general formula. So things like this, supposed to apply them and just move fast. So the moment you see an alkene, it has to be twice. Has to be. Because that's the general formula. So when we talk about burning, we're talking about adding oxygen because we know one of the things. In order for a fire to occur, oxygen needs to be present. Yeah? You have your lamp and you light it. I visited a friend, and one of the things that he now has is there's this little blow torch thing. You know, usually when you're in the country and the fire out, you take a piece of paper and you fan it. There's this thing that you can produce, just like the things that them use to blow the leaf. And you can just turn that on the fire, and in seconds, the fire blaze up back. Because again, the oxygen is needed. One of the things, if you're in a burning building, you're not supposed to mash the glass, you're not supposed to open the windows like that. Yeah, you have to go come out, but you have to be careful. Because a rush of air, fresh air, you just have to have that, something for us cause the fire to blaze. Now, every combustion reaction, no matter what the organic compound is, you must get carbon dioxide and water. So that's a must. No question asked. So once you see carbon dioxide and water are produced, it's a combustion reaction. So again, typically going across, subject, respiration is a combustion reaction. Remember glucose plus oxygen, give you carbon dioxide and water? Yeah. It's a combustion reaction. So here's the thing. To quickly balance, any subscript that is here, we just bring it in front of the carbon dioxide. Any subscript for the carbon, bring it right as the coefficient for the carbon dioxide. Any subscript for the hydrogen, we half it. A matter of fact, I don't want to take it for an advantage or disadvantage, or just to say that persons know what we're talking about. Going way back, when you learn to balance, technically, when you place a coefficient, it's really that coefficient times the subscript that gives you the amount of that atom. So it's really 4 times the 1. That's why we say we just put that and that balance the carbon. Technically, if you don't see a coefficient, there's a 1 there. If you don't see a subscript, there's a 1 there. So there's a 1 here, so it's 1 times the 4 give you 4 carbon. By doing that simple thing, only works with combustion reaction, you're balancing the carbon. To balance the hydrogen, half of what is there in the organic compound, so whether butane, ethane, you take half of that hydrogen, half of the hydrogen, right? And you put that as the coefficient for the hydrogen, sorry, for the water. So technically, if you look again, it is 4 times 2, which is 8, right? So would that be 1 times 8, which is 8. So by doing those first 2 actions, what you have successfully done is to technically balance the carbon and the hydrogen. So general thing, we normally just leave oxygen for last. And not only that, in this case, why we leave it for last, it's by itself. So let me explain that as well. If you try to balance, and it doesn't have to be for a combustion reaction, it's something that you can take across for balancing overall. If you recognize that you have a single atom that there's or a compound that no other element is attached to, leave that for last. Because when you put any coefficient, it's only affecting the oxygen. If you're trying to balance other things, that it's going to tamper with the other elements within the compound. So that's the principle behind it. So we know we have two oxygens, right? We know oxygen is diatomic, so we'll never have one of them. They will basically look for another atom of oxygen and bonds with it. Here, 4 times 2, we have 8. Some students, and I learned this recently, some persons are not even recognizing that elements can be in more than one compound in a chemical equation. So what you need to do is to add them. So oxygen is in the water, oxygen is in the carbon dioxide. So we don't treat them separate. So in the end, we have to go add them. So 4 times 1, remember, we're not seeing a subscript. So 4 times 1, 4. When we add them, we get 12. So from this, we know on our reactant side, things that are reacting, the organic compound and the oxygen, yeah, we have 2 oxygen. So there's 2 concepts. You can think about what is it, and persons probably figure out the answer. What is it that you multiply by this 2 that will give us the 12? Or you can divide the 12 by the 2 and you get 6, and you know that 6 would have been needed here. And your equation will be balanced because 6 times 2 gives us 12. And this works for any combustion reaction. You have situations where you may have a decimal and we have to do further steps. So we're doing it for that one. So we're going to also burn, just in case you're asked to burn. So the other one would have been butane. So what is the formula for butane? Butane.
So C4H6.
Sure about that?
No, H10.
And again, once we're burning, what are we doing? Adding oxygen. What do we get? Carbon dioxide and
Water.
same concept. Now, I'm also going to talk a little bit about both of these, the homologous series, the alkane and the alkene, in terms of burning. Now, 4 subscript, bring that to coefficient for the carbon dioxide, half, bring that to the coefficient of water. So we're running it again. That shows us that we end up with the carbons being balanced. 5 times 2, 10. 10 hydrogen. Hydrogen's being balanced. Now take your 2 minutes to balance using this concept. So we know again, if you notice, we are always, most of the time, I'm going to show you, I'm going to do the one for the alcohol. We have this situation now where I have 2 oxygen. 4 times 2?
8.
5 times 1?
5,
5 and 8.
13.
All right. So prime example, and this will allow us, and I'm happy that this one worked out like that so we can see the additional. If it is that we get an odd number, so that means we're going to, we follow the same principle, you know. What times 2 gives you 13?
6.5.
Right. Or you divide the 13 by 2, you should have get 6.5 and you bring the 6.5. We cannot have a point 0.5 within our chemical equation. And so what we do is to multiply. So this step is a given. Whatever you get. So if you get an even number, you don't have to do this step. Because you would have, just a while ago, we got 12, we would have used 6. If it was 10, we would have used 5, 14, 7, and so on. That ends our, our little balancing. But if you get an odd number, then you have to do the step where once you place the decimal in front of the oxygen, you multiply throughout by 2. So not every coefficient within the chemical equation. So there would have been a 1 here. So 1 times 2, 2. 1 times this. I'm just going to change the color. So this would now become 13, right? Did I say 1 times that? It's supposed to be 2 times 6.5, if I made that error. 2 times 4 would have been 8, yeah? 2 times 5 would have been 10. So the new, and let me just write, well, that one can stay. So the new coefficients that you would have had would have been 2, 13, 8, and 10. Now, as I said before, when you're working with a chemical equation, what you want to do is to leave spaces, especially if you know that you're going to be balancing. Leave spaces after the arrow because it's going to make your work messy. Now, even if that happened, guys, even if I have this, what would you do as a student? You have this. All you need to do now is to just put answer and you rewrite this just to be clear. So you don't want anybody, again, we are humans, we don't want anybody to, this is how you work out, or maybe you would have done this on a piece of paper because they would have just asked you. When they ask you to write the chemical equation, they're not asking you to show working. So they just want the chemical equation. So you could have worked this out on a piece of paper, right? And we have extra papers at the back of the booklet that you can do this on. Anywhere there, you just do it, and then you transfer the n on in the space that would have been provided for the answer. Cool? So let's see if the concept works with the, what was the alcohol? What's the name of the alcohol?
Methanol.
What's the formula for the methanol? Methanol.
Can go back, scroll up back to the top so I can see it.
And I'm not going to scroll up back. How many carbons does what and prime example no, because what would have been the
One.
and what is the general formula for alcohol? CnH2n plus 1 OH. Not true? So use
Yeah.
that to tell me the molecular formula. Because I need to show you something.
CH2OH plus OH. OH.
So question. 2 times 1 how much?
2
Plus 1 how much?
3.
So this would have been it, right? But if you're doing combustion, or I mean generally this, sorry, this is also your molecular formula. Yeah? Why? We can add the hydrogen from, and you have to do it for this so that it can work. You don't want to leave out the hydrogen. So this can also be burnt. Same concept. So let's see if it works. And for the alcohols, we have an additional step that we have to follow. So watch me now. Same thing. Subscript 1. We don't have to bring the 1 here. The thing about it, since we have a hydrogen within the functional group, to allow it to work, we have to take that into consideration. So we have to add the hydrogen into that amount of hydrogen before you can have. Because if you use 3, you would have end up with a, normally the hydrogens are going to be odd numbers, along with the 1 that is in the OH group will carry it to an even number. So we have 3, yeah, we would have had 5, we would have had 7. That's a typical arrangement. So we take into consideration, and even if you had it like this, it would have been the total hydrogen, which is still 4. But because we normally say the subscript of the hydrogen, I ensure that I put them into 1. So half of that would have been 2. And again, we're seeing the balancing. So let's work this. How much we have here? And watch me now. How much oxygen we have?
2.
We have 2 here. And how much we have on this side?
3.
All right. Check again.
4.
Everybody see the 4?
Oh, yeah, yeah, yeah. 4.
Yes, sir.
All right. Now, technically, watch what happens if you just say, all right, what times that give you 4?
2.
And I make sure do this incorrect to see if you'll pick up. But didn't the organic compound have an oxygen? Didn't the organic compound have an oxygen?
Yes, sir.
So technically, how many oxygens were on this side?
3.
All right. So here's the trick that you can do. Continue dealing with it like how you would have treated it. Let's see if I can bring down this and get it out of the way. Let me erase this. So whenever we have the alcohols and they too would have an oxygen, what we do is to operate similar, where we said this is 2. We just still operate. But we would have gotten 4 over here, right? Right?
Yes, sir.
So what do? Since we know that there's 1 over here, we want to take into consideration. So we are take out the 1 that we're going to give us the issue. So we take 1 out of that. Sorry. 1 out of that will leave us with 3. Why are we doing that? Because there's 1 oxygen that we want when we're balancing. We don't have to be focusing on. Yeah? Clear?
Clear.
So remember now, we said that we just want to focus on this, because if we keep on doing that, we're going to have to be placing coefficients in front of this. We can now just solely speak to this. The same concept now. Either what times 2 gives you 3? What times 2 give you 3? How are them there? Or 3 divided by 2?
1.5
Alright. And if we have a 1.5, what do we do?
times it by 2. I times all the coefficients by 2.
Alright. So there's a 1 here. So we times that by 2, we get 2. This 1.5, 3. Yeah. There's a 1 here. 2. 2 times this?
4.
4. So let's check. 2 times, we can do the carbon. We're seeing 2 carbons, not true? 2 carbons, so we carbon balance. Yeah?
Yes, sir.
2 times 4, 8. Yeah? That's from a hydrogen. Yes?
Yes, sir.
And over here, remember this would have been 4. I just the correct one now that I made adjustment. So 4 times 2.
8.
Alright. So let's check our oxygen now. So remember there's a 2 here and there's an oxygen in this compound. So 2 times this would have been 1. 2 times 1.
2.
And there's a 3 here. 3 times 2.
6.
6 plus 2.
8.
Alright. Watch me now. 2 times 2.
4.
And then 4 times 1.
4.
4 plus 4.
8.
So again, if it is a alcohol, remember those steps. So let me just go to the key points. We know this is because they can give you an alcohol to show combustion as well. We know this is the general formula. But when you're going to be writing, just include that hydrogen in the other set of hydrogens that are not a part of the functional group to give you the full number. Usually it will bring it to an even number. We have to remember there's an oxygen. So whatever number that you get here, so any amount of oxygen after you calculate it on the product side, just take 1 out of it. So if you got 6, you subtract 1, leaving 5 before you use it as the coefficient in front of this oxygen. So, and we know the outcome. So if it was an even number, we wouldn't have to use the 1.5. We wouldn't have to do the multiplication, throughout by 2. So if you got 7 hydrogens, all you do, subtract the 1, you end up with 6, you'd have placed 3. But if it's not an even number and you get an odd number, you have to multiply by a decimal to get whatever total oxygen. Then you multiply throughout by 2 and you must get the balance equation. Once you follow that concept, you're good. So here's the thing. They like to ask you about comparing those two organic compounds. The two in question are the alkanes and the alkene. So prime example, we said that butene is C4H8, while butane is C4H10. Now, the carbon to hydrogen ratio influence how the organic compound burns. And so alkenes burn with a yellow sooty flame. Popular thing that they like to ask you about. So one test that you can actually do to see or identify is not something that we normally practice in terms of as a major test, is to say that we burn both and see the type of flame. So because of the good carbon to hydrogen ratio within the alkane, we get a blue flame, a clean blue flame. And this is what Gaspro and those other companies bank on as a means of promoting their product. Because when you get that yellow sooty flame, it means that the carbon is not burning properly. And if the carbon is not burning properly, you're basically adding pollution. And if you're environmentally friendly, I'm sad to say some countries where we just couldn't care less. We just want we food cook. We just want to put the pot, or we just want the car burn or take away. But some persons look at those things. How is it detrimental to the environment? So alkanes, because of the good carbon to hydrogen ratio, it burns with a blue flame. And as I said, those companies will now ride on that and say, yes, hey, you get a blue flame, you don't get any pollution being added that will, be destructive to the earth. Alkenes, if you notice, the ratio of hydrogens are the same in terms of the carbon, in terms of it's not as higher than, because when we look back on the general equation or the formula, same in terms of doubling, but we have a little bit more hydrogen to a carbon ratio in the alkane. Now, just to add here as well, because since I'm looking at this, another way is to use potassium permanganate or bromine water. Now, one thing you should know about these two compounds is that alkenes are considered to be unsaturated. Alkanes are considered to be saturated. With those two terms, alkanes, they are not able to have any more, so if they're reacting, no other atom can be technically added. To add something or to get something in the compound, you have to substitute, right? And so alkanes undergo what we call substitution reaction. So whenever they're reacting, straight substitution. If something else is coming in, something has to leave. We can't have the two bull in one pen. One something has to go. Usually the hydrogens. So the hydrogens have to go. If something is coming in, hydrogens have to leave. Now, alkenes are unsaturated, and so there is a possibility. And when we look at the term, normally I just say to students, it's a situation where the carbon can accept more hydrogen. It doesn't have to be only hydrogen, but just to look at it. And that is due to the presence of the double bond. So in any case, any reaction, and we said it earlier, any reaction that the alkenes are going to have happening to them, it's going to be in the area where you have that double bond. So it doesn't matter if you're given ethene, propene, butene, heptene, whatever you get, the target area is going to be the double bond for every given. The only one that will vary is the fact that alkanes, everybody there's really just a single to single carbon bond. So the operation can happen anywhere. Appreciate it. Why? Because these double bonds are weaker. So if bromine comes along, he's not going to test. You know that bull in a pen that we play younger, when we were younger as Jamaicans, you run to the area where you see 2 weeks, Maddy, so you can bust out of the pen. You don't run to, you see 2 muscular persons holding hand. You're not going to run to that area. So right here is like that. Between these 2 carbons, bromine will attack this area because this is the weaker bond. And that's where you have the breaking of the double bond. Now, to appreciate this as a chemistry student, when this happens, you are now left with a situation where the carbons in question, right where the double bond is, they lack something to bond with. So right here, so carbon, going back to what we know, carbon has 4 electrons on their outer shell. These 4 electrons need to have a pair. So this and this one still pairs with, remember the hydrogen would have had, right? So that's the pair there. That's the pair there. These 2 carbons also, and I'm just showing you right here. So technically, this one is without a pair, and that's where the bromine comes in now. And that's why everywhere you have that reaction, when the double bond breaks, you have to go and present the atom that is being added. So they go through addition reaction. So right here, so we now have the carbons fulfilling their 4 bonds. So bromine water is actually reddish brown. So when you put it with an alkene, what the alkene will do is to react, and it will decolorize that bromine water from reddish brown to colorless. Yeah? Alkanes don't react with bromine water unless you have UV light. So what you can do, popular test, popular question, how to differentiate. So they like to ask how they could have given you these 2. So A and B are both hydrocarbons. How can we distinguish between these 2 hydrocarbons? And one way you can react it with bromine water, and don't mention anything else. So the alkene will react because of the presence of the double bond, while the alkane, no reaction. So that's another way to identify. So apart from the type of flame, you can look at how they react with bromine water and also potassium permanganate. So that is purple. And if you put it with an alkene, again, the alkene, due to the presence of the double bond, causes the potassium permanganate to lose its color. So it decolorizes. It's not going to happen with the alkane. Cool? So let me go again. So it says we're reacting B and D. B would have been methanol. D would have been an acid, propanoic acid. Acids plus alcohol under the right conditions will produce an ester. This is known as esterification, right? Now, oftentimes they like to ask to show this. So on the acid line or on the homologous series, the acids, sometimes this is a popular question where they ask you the acid reacting with an alcohol. So we should know esterification. The condition or the thing that is needed is concentrated sulfuric acid. So in order for it to occur, that's what is needed. So let's run through it. If you're going to be showing the reaction, you write it down. Draw the acid first. You have to draw the acid first. Draw the acid first. I'm going to say it again. Draw the acid first. And again, forgive me if I don't always put in the hydrogens, but you should know that hydrogens are attached. Now, just like overall, once you have the functional group, the reaction now go be between the hydrogen down here, so it now go be between the carbon here, because the functional group gets the spotlight. That's where everything happens. Usually for the acid, it's right here. This hydrogen. And we go back to it because we like take set on the weaker person. So you see that bond here between the oxygen and the hydrogen, or right here, the oxygen. Cause watch here. This is a double bond though, but it's between the oxygen and the carbon. It's not like a carbon to carbon. Let me clarify this. Remember the term for double bond for alkenes is between two carbon atoms. So students might ask me, sir, but you normally mention that, hey, that is a weak bond. Why not attack here? That bond was between two carbons. This bond is between a carbon and an oxygen. So here is where the target are here. So remember we said that this is the functional group. So these are the two areas that are targeted for a reaction with an acid. Either them attack here or they attack here. Now, when we're drawing the alcohol, we draw the functional group of the alcohol towards the acid. So we had methanol looking like this. Let me get this a little bit better. And it still not suit me as this pen is a challenge at times. So let me draw this first and then draw this. Alright. So bear in mind, and let me show you why. Because if you look back on the paper, this is how it is. So technically, we need to understand this. The functional group of the alcohol, it is the oxygen that is attached to the carbon. So even sometimes, even for me, sometimes I'm drawing and like I draw the OH and I do something like this. It's incorrect. Incorrect in the sense that it's really between the oxygen and the carbon. Yeah? So we draw it like this to show esterification. So here is the thing. If you look keenly, we did say that water is produced. So remember I talk about the bond? So right here, this is going to be removed. And if you look closely, this is actually H2O. Now, another point that I want you to remember, it's based on the question as well. Some questions will ask you to show the reaction. Some questions will ask you to show the reaction. Some questions will say, what is the product? So if them ask you, what is the product when methanol or when, in this case, B reacts with D, you don't have to go through all of this. Well, you can go through it to get to the product, but you don't have to show this. So again, key is reading the question is key and doing what it is asking you for. So if you not ask you to show the reaction of the alcohol with the acid, you doing all of that, wasting your time in the exam if you decide to draw it and then redraw it because you're showing, oh, may I try to get extra mark? No. Them just want to see the product. And bear in mind, this should be taken into context based on what the question is asking you for. So don't go and say your teacher did say you know have to show the reaction when the question says show the reaction. So if it asks if you show it, please show it. So the point is we go back to that same nature. Carbon, so if you look at this, carbon now technically, again, I'm just picking off this carbon right here to show you. So let's pick off that carbon. That OH is now gone. That's how we form the water. We know that this carbon now has a situation where it has an electron that it's not bonded to anybody. Let's focus on the oxygen now. Remember that oxygen that is bonded? It would have been bonded to the hydrogen because oxygen is in group 6. Means it has 6 electrons on the outer shell, meaning it needs 2 electrons to be shared to become stable. Meaning when this hydrogen now leaves, because this one of the electrons would have been being shared there with this carbon. There's one here with the hydrogen before in the alcohol, but since the hydrogen is now gone, that electron is lonely. This electron is lonely. To solve this, these two compounds are going to come together. So they are now going to form a join right where the carbon needs to get an electron to become stable, and this oxygen needs to get an electron to become stable. Other point, guys, if you're doing reactions on your test paper, and even for here, please, if you can get it in one straight line, meaning don't draw the reactions at the top and then draw sometimes I do understand. I know the situation because sometimes it even confuse me too, where you just get a little space. And some other questions, they get all 3 lines for just 1 word. Again, human beings that set the paper, sometimes these things are not looked throughout in its entirety. Some persons write larger than others. Some students, them write really small, so they can do it. Try though. So assess the space and put it in one straight line. So even for me, I not think this can work out for me right or so. But me I go try. So we would have end up, because I go just look away. And then I'm working with this pen and it's like it's on its own sometime. I'm just gonna put it right here. Change back the color. So taking my own little time. So here we would have now had the oxygen, right? So we get this. Now you remember that OH there? Sometimes students make a mistake and put back a hydrogen up there. It's not going to be an acid. So this is the product. So this is what I'm talking about. If the question says draw the product, this is what really CXC wants you to draw. This. Yeah? And if they ask you to show the reaction, then show the reaction. Usually the concept that I see them doing as well is to provide some boxes. So they provide a box and ask you to put it inside there. Now, the drawing, the acid portion will come first, followed by the alcohol portion. So acid portion, alcohol portion. Here's the thing, we also need to provide the name. So this is the ester. And the esters are named based on the acid and the alcohol from which they were formed. So typically, when you're writing the name, you do the drawing of the acid first, but the acid part of the name comes last. You do the drawing and the alcohol comes last, but in the name, the alcohol portion comes first. For in any case, the anal, remember this is the suffix that describes an acid, becomes "-ile". Anal becomes "-ile". Methanol, we get methyl. So methanol, becomes methyl. And we said that the alcohol portion is written first in the name, or said first. So this is methyl. So if it was butanol, it would have been butyl. If it was propanol, it would have been propyl. So in terms of the reaction, esterification, in terms of forming the ester, we just need to remember that. Yeah? For the acid, we get anoic acid in terms of the name. And that now becomes anoate. Anoate. So we had propanoic acid, it now becomes propanoate. So the name of the ester would have been methyl propanoate. And so there is, and if I highlighted this, it should be written really like that and that. Forgive me for this right here, which means it's a reversible reaction, which means you can get the ester and you're asked to state. So a whole heap of way them can come at you. But once you understand the foundation, you should be good. So they could have given you methyl propanoate and say, hey, draw the two organic compounds that led to the production of this ester. And you would have to know, say, hey, methyl, that means it's coming from the alcohol. So it was methanol. And so you draw the structure of methanol. Remember, you know, them not ask you to show the reaction. They must ask you to show, because they can ask you that too. And of course, you have propanoate. So it must have been coming from propanoic acid. So you have to understand the whole concept. So if I say hexyl butanoate, what were the two compounds that form this wonderful ester? Anybody?
Repeat your question, please.
What were the two compounds that form this ester?
Hexagonal and
So hexanol and
butanic acid.
so
Yeah.
butanoic acid. So wonderful. So if it doesn't, sometimes we're there, and so because it's a reversible reaction, and what they would have said, this is actually the hydrolysis. We're adding back water to the ester, and so we're now forming back the two reactants that form. So if we add water, technically what we're saying, the methyl getting its hydrogen, the acid is getting its OH, and they're forming back the alcohol and the acid. Cool? Now, gonna do our next another reaction, acid, and I'm gonna use this propanoic acid. And I can write it, I don't have to use a structure form. So let me use magnesium. Remember the concept. This is still an acid. And any acid plus a metal, what do we get? Acid plus metal. And if I want to be specific, acid plus reactive metal gives me what? An acid plus a reactive metal gives me what? So this is where your acids and base will cross. It can come over to the knowledge for organic chem. So I hear somebody ready.
For metal and hydrogen.
So
I mean,
usually,
salt and hydrogen.
thank you. So a salt and hydrogen, well, I may not be able to write out the word. Let's scribble it here. Hydrogen gas. So a lot of times students would have been able to tell me this if I had said, you know, sulfuric acid plus magnesium. It would have been different. Person would have quickly tell me, hey, salt and hydrogen gas. But because it's now with an organic acid, we lose that knowledge, but we're supposed to still remember it. Remember I spoke about the bond earlier? So this hydrogen, this is where it's going to attack. So usually we're used to having acids being written like this, where the hydrogen is at the front, in front of the anion, right? But for these acids, the organic portion gets preference. So the only one of the compounds where the hydrogen, which is the metal, the cation, is written last. So even magnesium, it's going to have to be written last, right? So it's something we need to remember. So again, just as though you have this being changed, that's how we get the name. And I choose to do this reaction because I want to get you familiar. So what will happen again, the magnesium is more reactive. It's like when we do what we call a single displacement reaction. So the magnesium is more reactive than the hydrogen. And so what it will do is to kick off the hydrogen and takes its place. So the propanoate ion, which would have been looking like this, supposed to be 2, right? So this is the propanoate ion. They are actually, these acids, they are monoatomic. So their charge is a -1, right? Remember, the magnesium is a 2 plus. And so since this is technically a polyatomic ion, you're going to have to put that in parentheses or brackets, have your Mg, then of course have your hydrogen gas. So just like this, the acid portion comes first in the formula, but the cation arrives last. But when you're saying it, the cation is said first. Magnesium propanoate. So that's the name of the acid. And again, we have to balance this equation. So we technically have 2 of this, and we have 2 hydrogens. And question students always ask me, sir, but we have more than 2 hydrogens here. We are talking about that hydrogen that was replaced. Yeah? So this hydrogen, because remember, technically, when you have this, guys, when you have this, acids will technically, what we call, dissociate or break apart in its respective ions. So the propanoate ion looks like this. And then remember the hydrogen looks like that. That's what forms the propanoic acid. Just as though if you had hydrogen and chloride. The only difference is you are writing the hydrogen at the end. Why am I mentioning this? Because you need to be able to be conscious that all of this is a polyatomic ion and it has a negative charge. So when you bond it with the magnesium, you're going to have that 2 and you put it in bracket. And so to balance this, we need a 2 here. Going back to the reasoning, students will say, hey, sir, you have 2 hydrogens here. Why not count up all the hydrogens? No, remember when this dissociate, this is one compound. The entire thing is propanoate ion. This is the hydrogen ion. So this is what you're multiplying to get 2 of it, and then the other part you're multiplying to get 2. That's how you get a balanced equation. This goes for every single acid. So the only difference, CXC may say ethanoic acid, methanoic acid, they can change the type of metal. So instead of magnesium, they give you sodium, they give you calcium. So you need to know that when you form the salt, this is how you're going to be writing the formula, but the name, the metal is said first, and then the acid portion, which becomes anoate. And so